All right, good morning, everybody. I haven't seen you since before the exam, really, unless I walked around your room that night. Exams are coming back to you this week in your labs. Take a few moments to look it over. I would certainly check your totaling. I would also check your answers against the common mistakes listing that we put together. Every page leader puts together what were the common mistakes and maybe a little detail about how we graded your consequence of the type 1 or type 2 error based on whether you said type 1 or type 2 error or something like that. So little details given in a few places where the common mistakes were to give you some guidance there. Come and address any questions you have by the end of next week, the 15th. We have this week and next week, and then one more lecture after that. 1, 2, 3, 4. After today, 4 lectures. That's it. So your final exam is the Thursday, the 21st of April, in the evening at 7:30, not 6 p.m. You get 2 hours. And your rooms will likely be different. We've got a few different rooms this time. There's a homework 8 out there. I'm going to give you a little guidance on that in a moment. Homework 9 will go up on Thursday on regression. Already going to warn you, the first 2 questions are many parts, but they are very good examples of what you could see on the final exam. They are questions that are the custom ones taken from an old final, put on the homework for you. And then we have one more topic next week called chi-square. They're my favorite tests. We'll do those together. And our last lecture will be just review. So we'll finish our material by next Thursday. And you can celebrate after you turn that pre-lab 9 in. That's your last one. No pre-lab for next week. Next week is a little more regression. One more example of that in your labs, and then some review in your last labs. No labs the very last 2 days of class, because there's no Wednesday. So next week is your last lab. Perhaps you've seen this already. Here's your summary of your exam 2 scores as a full class. Again, skewed to the left. Median is higher than the mean. Here's what I would do. Since either both of your exams are going to count or neither, take your 2 exam scores and add them up. Take that out of 150 points, and that's your grade right now on your exam part if it's going to be used. And remember, your 2 exams might be weighted 20% each, and your final 40%. Otherwise, your final can be 80%. We'll work out both of those methods for every student automatically. Then we take the maximum of those 2 methods and use that to work out your grade for you at the end of the term. All right. I have a little of homework 8 help for you, just kind of running through those questions and reminding you of a couple things. Any comments or questions about the exam or anything we've mentioned so far? I pulled up last semester's summary. Nothing changed here. Maybe a 1 point difference there, but it was very similar. Exam 2 typically comes down just a little bit, and then usually the final exam goes back up. That's what we see quite often from term to term. Oh, there's my other reminder. Today, statistics, open advising day. If you're at all thinking about or want to just learn a little bit more about the majors or minors or maybe one more class to take, we're available from 10 o'clock on right now. I'll be staying in my office after office hours today until 4 o'clock. So if you have any other stat question, you may stop by between 2 and 4 and I'll be there too. We can answer any question for you at all. All right. Little homework 8. Perhaps you have already started it, which I hope. If not, it is just 5 questions. So just a little recap on the questions, a reminder here and there. I did this with my Friday class last week, so I thought I would do it with you too. There's quite a few questions that just give you practice at writing up the hypotheses for a one-way ANOVA problem. H0 and HA. You know that hypotheses should be statements about the population parameters, not the sample statistics. We have in our notes a couple places, examples in ANOVA, where we've written out the H0 and the HA correctly. And so you just want to make sure that your statements are about the population parameters that we're studying, the population means, and that you also write the HA correctly, because that's not notation, that is more words. For at least one of those, population means is different. So one of them asks if proposed hypotheses are correctly written or not, and then you have to write them a couple times. That's in those three parts. Question 1 is the longer one. And in question 1, it requires you to do the ANOVA in SPSS. So when you bring up that ANOVA table in your output, you want to copy the table from your output file and then go over into your lecture book text box and paste it in. Because a table can't be exported as a graph or a JPEG. So we know that the alignment might be off a little bit when you paste it in, but your F statistic will still be there and your p-value will still be there, so you can do the rest of the problem. So you create that ANOVA table in SPSS, copy it in for one of the questions, and proceed to answer the questions about significance. What's the common level significance you should do for any basic H0 or HA for testing means or proportions that we've done so far? If we don't have an alpha, you should use 5%. And tests like Levine's test, those investigating tests to see whether certain assumptions hold, are usually done at a level of 10%. In that same question 1, you're asked to look at the Levine's output that's provided for you to assess whether the assumption of equal population variances can be assumed to be reasonable or not. And you're also given that multiple comparisons output, which was what we did after we ended up rejecting H0 in the first case, to say, yes, at least one of those population means is different, so now we can figure out maybe where those differences occurred. And you're asked to comment there. So question 1 is more of your typical final exam type question with lots of parts. You just have to create that one ANOVA table and use it to do your decision making. Question number 2 is just missing the F statistic, but everything else is there in the ANOVA table, so you just have to construct it. Remember, your F is that ratio of those two estimates of the variance that's common across the populations, those two mean squares. So you compute that, and it also gives you the box plots side by side as another way of checking the same kind of condition that Levine's test does for you about the equal population variances. So you comment on that. Question number 3 will require the calculator to come out. Question number 3, you actually have to compute the F statistic. Step number 1 and 2 of our 6 steps that we had gone through together in class. Step number 1, done for you because you have the X bars. You're given those 3 sample means, and you're given the 3 sample standard deviations in a little table. So that set of summaries is done for you. You're also given the overall X bar, which is the step 2. So the summary of the data is provided, not the raw data. And from those 2 steps, you're asked to then, let's work out those sums of squares to get those 2 mean squares so you can form your F. So that means the calculator out a little bit there. Just some practice at that. And question number 4. Question number 4 asks you to decide if ANOVA would be an appropriate procedure to do. So when is ANOVA used? When you have 2 or more populations, and you've gone to those populations and you've taken out independent random samples, and you've measured something that's continuous or at least discrete and quantitative, something that you can talk about the means of, that your response is quantitative. So do I have quantitative response, and can I assume that those samples look like they're independent random samples? That's what you need on the data side, and that's what you want to consider when you're talking about is the scenario appropriate to do an ANOVA in that case. The population side, of course, needs that the model's normal, and equal variances. And you can't really check that with just the description of the problem. Here's what I want to test, and here's what the data that I've collected. So you'll have to check those at some point, but don't assume that the normality or equal variances are what's wrong, because you haven't checked those yet. But look at what the data is that you have to work on and say, could I do an ANOVA on there, provided those other conditions are met? So you're looking to see whether you can assume you have independent random samples, and of course that your response is reasonable to calculate a mean for. Those are the two. So you're asked to say yes or no, ANOVA is appropriate or not, and you're asked to explain. So don't forget to do the explain part as to what part of those data conditions does not seem to be reasonable. Because I had one student email and said, well, it doesn't say anywhere equal population variances, so can I say they're not appropriate at all for any of them? Well, that wasn't the point. The point was the data that you have, would you even be able to do an ANOVA potentially on it or not? All right, so 5 questions for homework number 8 on ANOVA. Homework number 9 is just about ready. It'll go up on Thursday. Again, the first couple questions are longer ones, but very good practice. When you start to look at working for that final exam, there are 3 techniques that I haven't even tested you on yet. ANOVA, regression, which we're spending 2 weeks to do, and the chi-square test that we do next week together. Those are going to be on the final exam guaranteed. If you go to those old finals and you start to look at the regression problem, you'll find it quite readily. It's 2 or 3 pages long in that final exam, because 1 whole page is the output. And then there's some questions that follow. And if you start adding up the points from that regression problem that's on the final, that adds up to be quite a few points out of the 100 points on the exam. So that means the students that start studying from day 1 material and work their way through and then don't get to ANOVA, regression, and chi-squared well enough may lose those points too much. So master these last 3 topics first, and then of course kind of work backwards maybe, because our focus is on the inference side, and we learned the tools back in exam 1. But I want to make sure that you remember there will be for sure those other ideas in there, but the last 3 techniques that I haven't tested you on, there's a question for sure on each of those. All right, comment or question before we do turn to our regression material together. Question or comment? Homework number 9 up on Thursday, due the following Thursday, the 14th. Homework number 10, short. 3 chi-square tests we do. They're all the same kind of test, but 3 different ones, 1 of each. You do that one, that's an easy 30 points or close to 30 points, so that can be one you keep, and you drop one of the others instead. So 2 more homeworks still just to make you do it. I used to not make the chi-squared one required, and guess which questions on the final exam were the ones that they didn't do as well on? The chi-squared problems, because they didn't really make themselves do them when it was a required homework. So I still have that one being required. We drop 1 lowest homework score for you though. So if you decide not to do that homework 10, that's up to you. But I wouldn't recommend it. All right, where are we? We're in regression. We've been doing some regression last week, trying to come up with a technique for examining the relationship between 2 quantitative variables, often with the purpose of trying to predict one variable as a function of the other, hoping that there's a relationship and we can model that relationship so that that model could be used to make future predictions. We came up with this particular linear model, this equation of a line called the least squares regression line, that fit our 6 points fairly well to help us predict a final exam score as a function, a linear function of the exam 2 scores. We came up with the equation of the line, and then last Thursday we saw you'll be able to get that equation of the line out from the output. We used that equation to make a prediction. We plugged in some x's, got out some predicted values. We talked a little bit about the correlation, the value of R, where to find it in the output, that it measures how strong your linear relationship is, that it's absolute value is what's telling you how strong it is, close to 1 or minus 1. And its sign gives you the direction. And then we also talked about this thing called R squared, which is another nice interpretation in regression problem. 79% of the variability I see in those final exam scores, and they do vary quite a bit, 79% of this variability in the final exam scores can be explained by its linear relationship with X, with exam 2 scores. There's still about 21% that's not explained. That's due to other factors that influence your final exam score too. But that quantity, R squared, is also a useful measure of how well your model's fitting. The higher the R squared, the better. If I had 2 different models, I might compare their R squared to see which one would be a better fitting model. So far, we've been working with just the data and using the data to come up with a model to make predictions and kind of quantifying how well that model seems to be working. But we haven't done any formal inference where we're trying to necessarily predict for a population of values and things like that. And that's what we're going to do this week. So I want to imagine and talk about this difference here between the sample line that we have and this perceived population one. So here is our 6 students that we pulled those scores on their exam 2 and final exam scores to use to create our model. We fit the line that fits best to this, so this is our sample regression line. It's the one based on our data. Remind me, what were these distances called again? I'm just doing a little recap of what we did over this last week. Those distances of the points to the predicting line that we came up with based on our data were called the observed errors or the residuals. The observed errors or the residuals. And we actually found the line to make the sum of the squares of those as small as possible. Now, these are just 6 students, pairs of scores. Can you imagine that there really is a population of all such students, pairs of scores? And if I had every single student's exam 2 and final exam score, I could put them on this graph and it'd be very cluttered, but there would be sort of a cloud of points there. And if I did have every single value, so all the points were there for every single pair of exam 2 and final exam scores, it would be many, many points. And I could fit the line to them if I had them all. And if I did do that, the line might be a little different. And this line, though, would be called the true or population regression line. Now, the reason why I can't know that is because I usually can't look at every single item in the population. We usually have to resort to taking just a sample. But there is underlying this whole procedure the population line, the true regression line, if I had all the points. And my line is an estimate of that. Now, the true population regression line could also be looked at, and you could look at the distance of the points to that line. And those would also be called errors, but they would be called the true errors rather than your observed errors. They'll have a little different symbol when we describe them for the true regression line. So we're going to talk about this distinction that we're trying to use our sample to estimate a population. And in doing that, we can come up with an estimate of variability and do a little inference. Our main inference today is going to be this. Is the slope of our regression line that we have significantly different from 0? Because what would it mean if you had a 0 slope? What happens for every x that you plug in? You get the same value for your predicted. So using x doesn't help you. It doesn't help discern what you think the value of y is going to be. X is not a useful linear predictor. There's no significant non-zero linear relationship. That's what I wanted to learn. And so we'll be using our data to test that. Page 1, is it 92 that we're at? Which lists these 2 boxes that says, let's now move more into chapter 14 material, start to look at the inference side. And the first box is what we've been working with. We came up with the equation of this line. Probably a common error on the final is I ask for the equation of the line and most students forget the little hat over the y. or write predicted final exam score in words. But it is a regression line for making a prediction, and it's not the observed. We have our predicted value. The B0 and the B1 are the estimated intercept and slope. They're based on our data. And I'll be looking at my estimated slope and trying to learn whether or not it's close to 0 or not in a statistical sense. The population regression line has a little different notation. The population regression line says, here's how we're going to model the expected final exam score, the mean, as a function of x, as a linear function of x. The true average response is related to the x in a linear way, and here's these new quantities here, beta 0 and beta 1, which represent the true y-intercept and the true slope for the population line. We use Greek letter mu to represent the true population mean, and x bar represents the estimate. We have the betas here to represent the true intercept and slope for the line for the population, because they are the true values and the b's are the estimates of those. So we're going to be formally testing, is the true slope equal to 0? That's going to be our hypothesis, H0. So there is this underlying true regression line. There is a population basket for every person's X exam 2 score. And we're selecting a few values from those to come up with our estimated regression line. There are some conditions. We're going to kind of go through them here quickly. We'll review them again on Thursday when we check those conditions and give you a little checklist for what to do. But the concept is that every response you have, every final exam score is composed of 2 parts. One part is due to the population relationship, the fact that you had a certain value of x, and x is related to the response in a linear way. And then there's this other part that's due to the randomness, kind of like the luck factor. Sometimes on those exams you have a little good luck, sometimes you have a little bad luck, and it tends to balance out on average to be 0. But that's the randomness part. And that epsilon there represents the true error, the true difference of your observation, your response y, from that true regression line. The picture that goes along with this linear model in terms of what we model the responses as is a pretty nice one, because it's hard to draw it, so we wanted to put it in there for you. It says the following: every level of x is going to give you a population of responses. Think of the population of all students who got a 50 on the exam 2. There's all the students who got a 50 on exam 2, and in that population basket is their final exam score. What's the model for that population? Oh, it's going to be normal. We assume normal models for our responses in our populations. And it's centered around some true mean. That mean depends on x in a linear way. And then there's some standard deviation or variability, and I'm going to assume that the variability is the same no matter what value of x I started with. This sort of looks like it could be an ANOVA type of problem with 3 populations at 3 different levels of this explanatory variable, but we really have a whole continuum of populations along the x-axis. But the conditions are going to extend. We have normal model for our response. There's one more condition, that it depends linearly on that explanatory variable x. And then we still assume the standard deviation is going to be the same, no matter what population we're talking about. So we'll be checking for normality. We'll be checking for linear model through our scatter plot. And we'll be checking that we have constant standard deviation or variance. And we'll do that by looking at the data that we have to check these conditions about the population. So we'll do a little bit more on this. We'll kind of recap these ideas. But that's the visual picture, that we have normality for each population, linear model, and constant standard deviation. So the first thing I need to do before I can do some inference is to either know that standard deviation, sigma, or come up with an estimate of it. And most of the time we end up having to estimate sigma and end up doing some t procedures, which is what we'll be doing today. So these error terms are supposed to be what's left over after you fit the line, and they're supposed to be normally distributed with a constant standard deviation. And what we'll see together on Thursday is that the residuals play a big role. They're the estimated errors, the observed errors. And so we'll be checking conditions by making some plots of those residuals together. If you're checking normality, what's the common plot we would make to check normality? The population's supposed to be normal. You've got some values from it. You look and make a QQ plot of those values to see if the population looks normal. We'll do the same thing here. Our error terms are supposed to be normal. We've got some residuals. Let's see if they at least look normally distributed through their QQ plot. All right, so we'll run through this list here. We've done 3 of them. The other 3 we have to do through the rest of this week. We have estimated the regression line. We came up with our predicting equation. Every final exam that you look at, you have to know where to find your equation of the line from your output and pull it out. So you can use that equation to do some predictions. We have measured how strong the linear relationship is with the correlation, that value of R. We have made some predictions by plugging in x's. Our little caution there was to watch the units, and we don't want to extrapolate. Extrapolation is where you're asked to maybe make a prediction for a value of your x that's way outside the range of where you did the modeling. You created the model for x's between 30 and 50, and then you're asked to make a prediction for 72 for value of x, and that might be out of range and be a little risky. What we have left today to do is assess that we have a significant linear relationship, get a little started on making some intervals for our predictions rather than just the best guess. And Thursday we'll be checking the assumptions more formally and doing a full regression problem together. So that's where we're going. So to do some of the inference, we need to have a good estimate of that standard deviation of how far away the points are from the line. Well, we can do that because we have our line, that's a good estimate, and we have those things called the residuals, which are how far away those points in our data set are from the line. So we're going to estimate the standard deviation, which reflects how accurate our predictions are, by looking at the sort of average size of our residuals. How far away are the points from the line on average? So we know that if we actually took and calculated the residuals and added them up, they add up to 0 because they keep canceling each other out. So we got to round that by always doing the squares. So we're going to take the sum of the squared residuals and add them up. And you always take a sum of squares and divide by an appropriate degrees of freedom to kind of form your S, your variance term. Degrees of freedom usually are n minus 1 whenever you have a single set of data, but here they're going to be n minus 2 for regression. And the 2 comes from the fact that you had to use your data to estimate 2 things to come up with your equation of the line. You had to estimate beta 0 and beta 1 with your data. To come up with the predictions, you had to use your data to estimate 2 terms, not just one overall mean. And so every time you throw in another explanatory variable into your model, you lose 1 more degree of freedom in terms of the variance estimate. So n minus 2 is the degrees of freedom you'll see everywhere on that yellow card for regression. When you take a sum of squares over the degrees of freedom, you get a mean square. The mean square for the residuals or error. And of course, I have to take the square root of that if I really want an estimate of the standard deviation. Now, we calculated the sum of the squared residuals together last week. I'll never have you calculate that in raw form on the homework or the exam, because that means calculating every residual and squaring them and adding them up. You will likely have to find one residual, just so you know the definition of it, but not all of them. So this will be found in output in 2 places. The output that you have below shows you those 2 places. It is a summary about the model, your S for the regression line, a quantity that tells you how far off your predictions will be on average, is right there in that model summary. There's S, 8.24. If we used our equation that we have come up with to make predictions about final exam scores based on your exam 2 scores, our predictions would be off on average a little more than 8 points. Okay? Predictions could be plus or minus about 8 points from what they actually turn out to be. And then there's another place we get that, through the mean square. The mean square for the residuals, right there, 68. Mean square for the residuals or error. So that's not S, that is S squared. If you take the square root of 68, you get that about 8.3. So there's two places where you can get this S for your regression line, this average size of the prediction errors. How far off will your predictions be on average? About 8.25 points. You use this S in a lot of our confidence intervals and prediction intervals that you'll see in a little bit, so you want to be able to pull that off. Now the fact that we have to use S and not sigma means we're probably going to do a t-test of some sort rather than a z-test. And that's exactly what we're going to do to answer the classic question in regression, which is, do I have a significant linear relationship between my two variables? There's what the H0 and HA look like. Is the true slope for the regression line, for the population model, equal to 0 or not? Because if it were equal to 0, what happens to that true population model? If the true slope is 0, then the x part of the model comes out completely, doesn't even enter in. If the true slope is 0, then we would predict or estimate the mean to be the same thing for everybody. Knowing the person's x doesn't help to discern what you think their response might be. So we use this set of hypotheses to test the classic idea, does my variable x help to predict my response in a linear way well? We'll do that through a t-test. We'll need our best guess for that true slope, and we have that, our b1, our estimated slope. We'll subtract off the null value, which is usually 0, but it doesn't have to be. We might be wanting to test, is the slope 2, because last year it was 2, and is it changed? And then we'll need some kind of standard error always on the bottom. And that standard error will involve the S that we just talked about. So you've got a nice summary box for this standard t-test that's done in regression. There's your t-statistic. Here's the standard error for the slope. You need the S for the regression line to tell you how far off your predictions will be on average. And then you've got that sum of x squared terms down there. This summation we had a little shorthand notation for. That was SXX. We found that back in our first calculation table together last Tuesday. And if you look at the old exams, I also give that quantity to you. All the outputs there, but nowhere in SPSS output do they give you that particular term. It's used in a lot of the numbers that are there, but it doesn't give you that term directly. And that is one you need quite often for a lot of formulas, so we'll give that to you. And the degrees of freedom are always this n minus 2. We, of course, could modify the hypotheses. We could do a one-sided test. We could do a one-sided test with 0 or with the value of 2 or any number we want. So the t-test is very flexible. It can do any hypothesis test you want regarding the true slope. So let's try it out. Let's answer our questions here. Do we have a significant linear relationship between exam 2 scores and the final? Is exam 2 a useful linear predictor for that response? Let's test the classic hypotheses in a regression problem at a 5% level. So the first quantity that I need to find, because I don't have it yet, is the standard error of B1, because I'll need that for my t-statistic in the denominator. And it says I need the S for the regression line over that SXX quantity. Now, just the page before, we looked up that S. How far off will our predictions be from the actual values, about 8.24, wasn't it? 8.24, carrying it out a little bit, 671. That was from our output for the average size of the residuals. And then you'll have to go back. What page was it? Page 186. And find that summation term that is going to come up in all of the formulas that we use today. That summation on the x's. So from page 186, we should have this summation term, one of the column heading totals, 940. So that's going to give us our standard error of how much? About 0.269. Now, do you know how to interpret a standard error? Standard error of x bar, standard error of p hat. They all have the same basic structure. You always use a phrase, well, we would estimate the average distance of the possible values from their mean to be about this much. So this is the standard error of B1. We would estimate the average distance of the possible slopes, estimates, possible estimated slopes, from the true slope to be about 0.269. There's only one estimated slope that we have so far, the equation of the line that we got with our estimated slope. But if you were to do this whole procedure again, take another 6 students, get their exam 2 scores with their final exam scores and fit the line to them, your line's going to be a little different. For every set of 6 students that you select randomly, those slopes, those B1 values are going to vary. And they vary around the true slope, but only are off by about that much on average. That's the yardstick. All right, so that allows us to assess whether or not our estimated slope, which was a little more than 1, is really different from 0 or not. Our equation of the line, our estimated slope, was what? 1.046. I mean, 1 doesn't seem to be that different from 0. But how far away from 0 is it when you use your standard error yardstick on the bottom? So when you divide by your standard error, you get a t-statistic of 3.89. Now, don't you already have a pretty good sense about what we're going to say here then? Now that we've done so many t-tests, and we know t-distributions, and they're not that far off from a standard normal, when I'm talking about a t-statistic that's close to 4, that my estimated slope is nearly 4 standard errors above 0, that's pretty significant. I expect the p-value to be quite small. And right now we would have to use our table A3. And from table A3, our p-value could be found, or at least bounds for it. That's a terrible t-distribution, but that's okay. How many degrees of freedom, though, do we have here? Remember how many students we had in our data set? Only 6. So our degrees of freedom are going to be 4 and minus 2. We're way out here at 3.89, and I want that tail area to the right, but also the tail area to the left, which would be the same. Now, the largest t-statistic that's even in your table is a 3. And so if we have a 3 as our value, and the 3 that's there already gives us a pretty small tail area with 4 degrees of freedom, how much is that? 4 degrees of freedom, that tail area to the right is 0.2. So from 3 over to the right, it's 0.02. I would like the area to the right of almost 4, 3.89. So that's smaller than 0.02. This one over here is smaller than 0.02. So my total p-value, I can say, is definitely less than 0.04. That's the best I can do with the table. It's actually much less than that. But I can say our p-value is smaller than 0.04, and that's still enough for me to make our decision. what would be my answer to these two questions at the top, where we were asked to assess if we have a significant non-zero linear relationship? Is X a useful linear predictor? Our answer to both of those would be yes. Our p-value is very small. We would reject H naught. Rejecting H naught tells us it looks like the slope is different from 0. So it looks like your exam 2 score is a useful linear predictor. Certainly could add maybe other variables in the model to do better, but it is useful. All right, so our one clicker question is coming up for the day. It has to do with the think about question on the next page. We just made a decision regarding the significance of our linear relationship here. Question first. The basic hypothesis is two-sided. Now, I might be more interested in doing a one-sided test here. I certainly would hope that exam 2 scores and the final exam score are not negatively related. I would expect only a positive type of association. So if you do have that theory up front, then you test that and do a one-sided test. And you could do that here. The t-test is the most flexible. It can do any test you want, one-sided or two-sided. But the classic one, the one that's in the output that we'll see in a moment, is the two-sided version. Now, another thing we can do, we know, is make a confidence interval. And confidence intervals can be used to do hypothesis testing if things match up okay. And the question here says, well, we just did a t-test at a 5% level of significance. So what do you think about the 95% confidence interval if we were to make it for the true slope, for values of what the true slope could be at a 95% level of confidence? The question is, would it contain the value of 0? Yes or no? Think about what you just decided. We had a small p-value on the previous page. We made a decision about that true slope. So you should know whether value of 0 will be in the interval or not at a 95% level of confidence. And not doing too bad, but it could be closer to 100%. We just rejected the H naught that said this. No, right? And so we said it's not possible for 0. We would say no to 0. It should be a no. We know that if we were to make the confidence interval, 0 would not be in it. How would you make the confidence interval? So you could test any hypothesis, perhaps, that's two-sided you'd want. Well, what you would do is start out with your best guess. B1. What did you get for your estimated slope? Go out from that a few of its standard errors. So you could have a range of values that are reasonable. Our best guess was a little bit more than 1. Our standard error that we calculated on the previous page was 0.269. But the only thing left to do is look up the right t-star value. And you know what I've seen students do? The output is there in front of them, and they're doing a confidence interval, and they pull off the t from the output and put it in there, the t of 3.89 that we just calculated together. But that's your t statistic that's based on your data. That's not your t-star value. Your t-star value is a particular percentile. So there's 95% in the middle that you have to look up from your table A2, with the 95% level of confidence that you want. Degrees of freedom here, and -2 again, or 4 degrees of freedom. So this is a 2.78, if I looked that right in the table. And a margin of error that would go out about 0.7748. There's your margin of error. So our range of values that are reasonable go from about 3/10 of a point all the way up to about 1.8 points, 1.794. 1.794. I would estimate the increase on the final exam to go up by about 3/10 of a point to about 1.8 points for every additional exam 2 point that's earned. And I can see 0 is not in that interval. In fact, you would be able to very quickly test these hypotheses for me. I don't know why I'd want to test whether it's 2 or not, but maybe the model last year that was created had a slope of 2, and I want to see if things have changed from that model. Could the true slope be 2, or do you think it's not 2? And here's your interval. What would we do? Stay with H0 or reject H0? 2 is not in here, so I would reject H0. We know that the p-value would be small for that hypothesis test, and you could simply look to see if that value is in the interval. But 1 would be acceptable. 1.5 points would still be acceptable, and so on. The key is that it's a two-sided test, and you're doing a test at 5% with that 95% confidence interval. All right, would you be able to interpret the confidence level here too? Would be the same start for the most part as we gave you on that exam. If you repeated this whole experiment, the study, again, many times, and for each time you do it, you made a confidence interval for your true slope. Here's the one we got this time, and then we do it again, and we get a slightly different interval. The intervals will vary. What can you say about those intervals? 95% of those intervals would contain the true or population slope. Beta 1 is your new parameter here. 95% of the resulting intervals would contain the true slope, beta 1, that true parameter. All right. Where do we find this stuff from our output? A couple places. The coefficient section of your output is the biggest part that gives you your equation of the line. There's where you find your y hat model. Very important part. So I can use that to make predictions. The inference that we've been doing is all about the slope. So the primary row that I'm going to focus on is the one that says exam 2 scores there in the beginning, because this is information about the coefficient of exam 2, which is the slope. This is B1, your 1.046, and what sits right next to it that we calculated by hand just a minute ago. There's the standard error. So yes, you have the formula for the standard error on your yellow card with that summation of the x term that you might have to look up or work out, but the standard error is already found for you. And doesn't this look a little familiar too? There's the test statistic. We got 3.89 when we did our calculations by hand. 3.888. And right next to it, there's the exact two-sided p-value for testing if the true slope is 0 or not 0. We only came up with it's less than 0.04. Well, how much less than 0.04? It's actually in the two tails together 0.018, 0.009 in each tail. So you have the exact results there. You could make your confidence interval very easily using these two numbers. You just have to look up a t-star value. You have the test already done for you right there. Report that test statistic and that two-sided p-value, and you don't have to look up anything from a chart. But then there is this other t-statistic here, and p-value, that I just want to highlight for a moment. Not always looked at that much. But the t-statistic in that p-value that's in that top row is about the intercept. That t-statistic and p-values formally testing, is the true y-intercept 0 or not? Would you have to have your equation be such that when x equals 0, y should be 0? Go through the 0, 0 point. And in some cases, it makes sense that that would have to be the case. So if you're interested in the intercept term, if it makes sense to talk about it, if you can talk about the value of your y when x is 0, and that's a meaningful quantity, then you might be interested in testing that hypothesis. But that's one that's not as common as the one about the slope instead. And then the final way to do the same test we've been talking about, the test for the slope term that we are interested in, is the slope significantly different from 0? That particular set of hypotheses can be tested in a third way. T-test, confidence interval, see if 0's in it, or what is called the F-test in regression. And the F-test in regression is through the ANOVA table. There's an F statistic sitting there, and look at the p-value. It's the same as what we just pulled out from the t-test, which it should be because it's testing the same hypotheses. Here's the idea. If you were doing the t-test, and you did your hypothesis test where you got what, the 3.888, and we found the p-value as those two tails added up, those two together were 0.018 under our t distribution with 4 degrees of freedom. If you did the F-test, remember what an F distribution looks like? It's skewed to the right. This particular F distribution that we're working with would look like this. I know I usually draw them with a hump, kind of a mode, but it would actually look like this for a 1 degree of freedom and 4 degree of freedom F distribution. And if you were to take the 15.115 and find the area to the right, as you do for p-values with an F-test, you would get the same, 0.018. Because there's a nice relationship between the t distribution here and the F distribution here. The 4 degrees of freedom goes in the second spot, and you have 1 degree of freedom here. If you were to take your t statistic and square it, 3.888 squared, you would get about 15. You would get your F. But the F statistic that we're reporting here and its p-value only can be used to test the equal to 0 versus not 0 hypothesis. It can't do anything else. It is only able to test that two-sided alternative. The F distribution only looks at the area to the right, and that p-value is for the two-sided alternative HA only. So the F statistic is the most restrictive. It can't do anything else besides test those theories. The confidence interval is a little more flexible. It could be used to test any two-sided hypothesis you want. See if the number's in your interval or not. The t statistic and its test is the most flexible. You want to do a one-sided test instead? We can do that. Just take the one little tail area here for a one-sided test if it's to the right of your t statistic. You can do a test about 2 versus greater than 2. You can do any test you want. You just have to adjust your test statistic, but you can use it to do any hypothesis test about the slope. So if you're doing the classic one, I'll have two answers that are possible. For give me a test statistic, give me the p-value. The p-value has to be the same, but the test statistic could be the F or the t. But if I were testing for greater than or less than one of those directions, you couldn't do the F test anymore because it's not designed to do a one-sided alternative in that sense. All right, here's the pictures of the day. My daughter does not have school this week. Her and her lunch buddies that eat lunch at the same lunch table every day for the last 2 years in middle school all came over and had pizza and ice cream and such, and they had a serious picture and a silly picture. And now she is at other kids' houses during this week, so I don't have to worry about her. All right. One more topic for today, about another 10 or 15 minutes at the most. And what's nice for Thursday? Checking assumptions and a full regression problem. That should help you quite well with your homework 9. So we've gone through to assess that our linear model is significant. That exam 2 scores are a significant linear predictor for the final exam score. So how would we predict Barb's final exam score if we know that she scored 60 on exam 2? How would you make that prediction for a single student? We would plug in 60. We would take the 2167 and our slope times the 60 points she earned on that exam 2 and get her predicted value out. And we did this prediction earlier. We did it for right after we found this model, and we got about 84 points. We would predict Barb's final exam score to be 84.43 points. And that would be her prediction. But then if I had asked, well, let's consider everybody who scored 60 on exam 2. So all the students, not just Barb, but everybody. So consider them in a population. Here's all the people who scored 60 on exam 2. Here's their final exam scores. Let's estimate the mean. Let's estimate the mean final exam score for everybody who scored 60. Well, I would still use my model in the same way. My model is used to predict a single person's score, but it also could be used to estimate the average for everybody that was like that person, that had a score of 60 on exam 2. So we would still plug in the same 60. We would still get out 84.43 points. Now that's not really a single y being estimated, but rather the expected value of y. Here's what your textbook would use. It would put a little hat over the expected value of y. Or in some other cases you might see, we'd estimate the average response for everybody who scored a 60 to be 84 points. What we're saying is if you had that population of everyone who scored 60 on exam 2, we would estimate the mean of that population to be 84.43 points. And now Barb's coming out of that basket, and we of course would predict her score to be what the average is for that population that she came from. But these are two different estimates. One is for predicting a single person, the other is for estimating the mean. And those are different questions that have different variabilities behind them. It's a lot harder to predict for an individual. Individual scores vary. Averages don't vary as much. We learned that back when we studied the CLT and saw how individuals have a sigma, but averages have a sigma over square root of n. So that's the concept we want to highlight at the bottom here. Estimating or predicting a future observation versus a mean, same value, but they're going to have different standard errors. And their standard errors will be based on how easy it is to predict versus estimate a mean. So going back to our pictures we actually did with CLT a while back. Here's an original population of individuals. Here's our population of individuals. There's some mean for that population, some standard deviation for that population. We represent those by mu and sigma. And then let's consider the population of means, of averages, kind of like of x bars is what I'm highlighting here. And we know that averages still should vary around the true mean, whatever that might be. But we learned that averages, though, don't vary as far away from that true mean. That amount of give or take got to be reduced by the factor of how many observations you selected, your sample size. So the standard deviation for individuals was sigma. The standard deviation for means, you got to divide by the square root of n. Which one is larger? It's much larger for individuals. Individuals will have a larger standard deviation. So we're going to calculate, before we leave today, two intervals. One of them is going to be a prediction interval for an individual response. Here's our best prediction, and then let's go out the plus or minus to make the prediction interval for that one person's value versus the confidence interval for the average response. So those two intervals are going to be made. Which one is going to be then wider versus narrow? The prediction interval is going to be what compared to the confidence interval for the mean? Individuals vary more. They have a larger standard deviation. So when it's a prediction interval for an individual, it's going to be wider. And the formulas are atrocious on the next page. Yuck. You can have SPSS make them for you for the x's you have in your data set, which is nice. But there they are, and they are both on your yellow card. And I don't ever have you do both of them on a final. If you do one, that's enough. Many of the pieces of the quantities here you have to be able to plug things in. Let's take a look. And notice that we call them different things. We call them a confidence interval for the mean. And I distinguish that by having a prediction interval for individuals. So I'll even ask specifically for one or the other, and you shouldn't get them mixed up. Confidence interval for the mean versus a prediction interval for an individual. Now the confidence interval for the mean is at the top, and it's got your y hat as your best guess, and you'll look up a t star still, just like we did a few minutes ago. And the standard error is for the fitted regression line, which is fitting what you think the mean response will be and how it changes with x. Standard error fit for the fitted regression line. And there's that formula for it. You need the s. Didn't we show you where to find that in a couple places in the output? The s for the regression line. You need the sample size, which of course you'll have given. You need the summation that we already used once together. That's that SXX. And I did say I would give that to you. If you look at the old exams, here's all the output, and also SXX equals. And I'll find that for you rather than you having to compute that yourself. And then the top, though, has a particular x minus x bar. And I get a lot of students thinking, why don't I just cross those out? Don't they cancel out? But the top is the x that you're predicting at, the x you are estimating or predicting at, so in this case the 60, and then the average is the x bar for the data set, the average exam 2 score that you plug in there. So it's the distance of the particular value that you're estimating at from the mean. Notice that if I were to have you do a confidence interval or prediction interval, and the value of x that I have you plug in is the mean at the actual average, then that whole term on top will fall out. You don't even have to worry about that part. All right, and then you take that standard error fit, which is for fitting the regression line, and then you add to it another variability piece because individuals vary more than averages. So you find your standard error for the prediction for an individual by taking the variability of the points around the line, that standard error fit, and then here's this extra squared that you throw in there because individuals have that individual standard deviation component that make them vary a little bit more. It is that extra piece right there that makes this a larger standard error, that makes your prediction interval wider. So let's do it. Let's make it for our confidence interval and prediction interval when someone scores 60 on exam 2. So we first are going to do the confidence interval for the mean. We already found our predicted value, which was what? 84.43 points. And then I have you look up a t-star just a moment ago. The t-star value for 4 degrees of freedom and 95% was 2.78 from table A2. And now I need that standard error. The standard error for fit. It requires the standard deviation around the regression line of 8.24. I need 1 over the sample size, which was just 6 observations. I need that SXX term, which we looked up a minute ago from our calculation table of 940 in that denominator. And then the top is looking at how far away is the x that you're making your estimate at, 60, from the average exam 2 score, and that average was 51. So if someone's value of x is really close to the average of the x's, or even equal to, then that term is really small on top. That becomes pretty small. If you're trying to predict or estimate for someone and they're really far out from the mean, that's harder to do. Makes the standard deviation larger. All right, now it's just calculation. In fact, one of the old finals even said just plug everything in and leave it. That's your final answer right there. Because I know you could then work it out, rather than taking the 2 more minutes to work out that whole standard error. But let me give you the details so you have it in your notes once here. The standard error part, when you calculate all of that, would turn out to be 4.147. So the margin of error, the entire plus or minus part that you go out from your estimated final exam score average, is 11.53. And so here's the range of reasonable values for what the average on the final exam could be for everyone who scored 60 on exam 2. It would go down to 72, almost 73 points, and go all the way up to almost 96, 95.96 points. We would estimate that if someone scored, for the people that scored 60 on exam 2, their average on the final exam could be anywhere between 73 and 96 points. It's still quite a wide range. Still could get an A+. All right, so there's the range for what we think the average on the final exam score could be for everybody who scored a 60. What's going to happen when we make the prediction interval? This is our last calculation today. We know that the prediction interval is going to be wider. Confidence interval, prediction interval. Prediction interval is always wider because it's always harder to predict for a single person. You've got to go out an extra plus or minus with that extra s squared. So the prediction interval is going to still be centered at the 84 because that's our best guess for individuals that come from that 60 exam 2 score population. We'll go out the 2.78 still. But now that standard error has the extra s squared in it. So we take the standard error that we had, and how much was that? 4.147 from the first one. There's that standard error. We'll square that because we have to pool together the variances and then take the square root at the end. Here's the extra s that's going to be involved because we're predicting for an individual. The 8.24 term gets used again. There's that extra s squared part. Pool those together and get the overall standard error for the prediction. That overall standard error is 9.23. That gives you a margin of error of 25 points. 25.66. Here's the prediction interval. Here's what you would predict for possible values for individual person who scored a 60 on exam number 2. Anywhere from 58 points all the way up to 110, which of course is not possible because it's out of 100. But there's still quite a wide range there. We only had 6 observations behind this predicted interval. And so there's quite a wide variety. It's potential to do quite well, even if you only got a 60 on that first exam. You're done. I'll draw this picture next time. 4 lectures left. See ya.